So in our last video, we looked at operators and eigenfunctions and eigenvalues, and we looked at examples of situations where when we operate on a function, we got a constant times the original function, which meant that function was an eigenfunction, and the constant an eigenvalue, which would be the result of a measurement in the lab. We then looked at an example where we got a situation where the function was not an eigenfunction. So what do we do in those circumstances? Well, in this video we're going to look at that in more detail. So we're going to go back to our document on the Schrodinger equation, and we're going to look at a function, the square root of 2 times sine of pi x. Now you might recognize this as being very similar to the particle in a box function, which in fact it is. It would correspond to the n equal 1 level for a particle in a box of length 1. So we have our function, and let's see what happens when we operate on that function with our momentum operator as defined in the previous video. Just to review, the momentum operator was defined up here, h bar over I times the derivative with respect to x. So that's our momentum operator. And when we operate on our function with our momentum operator, we get this result. Now, if we take a close look at this result and ask now, is there a function psi1 an eigenfunction of the momentum operator? Well, so we start out, we notice first of all we've got a constant, and that constant has the imaginary number square root of negative 1 here, which might clue us in that there's going to be a problem, but be that as it may, we take a look here. The big deal is that we have a function which is not the sine but the cosine, so we do not have the original function here. When we operate on the sine function with the momentum operator, we get a cosine function. It's a different function, and therefore the sine function is not an eigenfunction of the momentum operator. So what does that mean? Well, as I explained in the last video, that means that right now we don't know what the outcome of a laboratory measurement might be, because if we have an eigenvalue, then we know if we go to the lab and measure momentum, we're going to get the eigenvalue as the result of that. But we don't have that. So what does that mean? Well, very simply, what it means is that there's more than one possible outcome for our measurements in the lab. We're not going to get just one value, we're going to get multiple values. Still, at this point, we don't know what we're going to get, and we'll talk about how we determine that in a little bit. But the outcome as of this point is uncertain. We know they're going to get several possible outcomes. We don't know what they are, and we don't know what their probabilities might be. Let's just take another look. Let's look at this function again, but this time do it with the kinetic energy operator. So we will operate on psi1 with the kinetic energy operator in the x direction. And when we do that, we get this result. Again, we ask the question, do we have an eigenfunction? Well, yes, in fact, we have an eigenfunction. We'll note that our original function was the square root of 2 times the sine of pi x. So we do have the sine of pi x here in our result. So we know we have the sine function there. The question is, what is the eigenvalue? Now, it is not pi squared h bar squared over the square root of 2m, because remember our original wave function had the square root of 2 in it. So we can do some simple algebra here just to extract the eigenvalue. One is, the simplest way to do it is just to very simply divide out our result here by our original function, and we can do that easily enough. The percent sign in Mathematica means that we are using our last result And if we divide by our wave function, what we get after dividing our result out by the wave function, this becomes our eigenvalue. And again, you see it's a constant, pi squared h bar squared over 2m. That would be the kinetic energy of our particle. All right. Now, so here we have a function that is not an eigenfunction of the momentum operator, meaning there's more than one possible outcome, but is an eigenfunction of the kinetic energy operator. Well, you might ask how that can be. Well, and we'll get a little bit more of a clue of this on this when we do our next exercise, but remember, momentum is a vector quantity. And so we have a situation where momentum can be in a plus or minus direction. It can have a plus or minus value because it's a vector. But because the kinetic energy is related to the momentum squared, the total kinetic energy is the same. Doesn't matter. The sign doesn't matter. The direction doesn't matter. So here we have a situation where we might suspect is what we have a particle. We have a particle which has two possible outcomes to momentum, one going in the plus direction, one going in the minus direction. Both of those have the same kinetic energy. So there's more than one outcome for momentum, therefore it's not an eigenfunction of the momentum operator, but only one outcome for kinetic energy, and it is an eigenfunction of the kinetic energy operator. So we will actually then stop here and take a look at what happens in the lab and how we deal with these situations when we look at the possible outcomes of our measurement.